All right, so we're going to start with Chapter 3, Section 2, and we're going to start with, this whole section is about least squares, regression lines. So hopefully some of this, especially the beginning, will be a review from Algebra 1 when you first were introduced to regression lines. But again, you know that y is your response variable and x is your explanatory. So a regression line will have the form y hat equals a plus bx. Y hat means the predicted value of y. It's important that you always put the hat on y. If you just put y, that means the actual value, and we're actually looking for the predicted value when we use the regression line. B is your slope. Notice that it's the variable with x, so it's your slope, and it is the amount by which y is predicted to change when x increases by 1 unit. One thing to remember when you're interpreting slope, and this, again, this from Algebra 1, is your rise over run. So your change in y over your x. And then A is your y-intercept. So this is the predicted value when x equals 0. One thing to keep in mind, on your formula sheet, it's not in this form. Your formula sheet is y hat equals b with a subscript of 0. So that's your y-intercept. And your slope is b with a subscript of 1. And that's your slope. So that's the form you'll see on your formula sheet instead of the a equals bx. So here's an example of a regression line. This problem is about non-exercise activity and how many calories you burn, and then your fat gain. So the equation is 3.505 minus 0.00344. NEA just represents non-exercise activity. So that's your explanatory variable, and fat gain is your response. So instead of using x and y, it actually used the variables, and that's fine. If you're going to use x and y, you have to write down x equals the NEA change and y equals fat gain. So just make sure you indicate that. Sometimes you'll be asked to interpret your slope and your y-intercept. The easiest way to interpret slope is to write out 0.00344 over 1. So it's the change in your y over x. Remember, y is your fat gain, and x is your non-exercise activity. So as fat gain increases 0.00344, your non-exercise activity increases. So that's going to help us to interpret it. So it tells us the amount of fat gained is predicted to go down by 0.00344 for each added calorie of non-exercise activity. So rise over run, the change in y by the change in x. And then your slope is when x equals 0. The y-intercept is the fat gain estimated if the non-exercise activity does not change when a person overeats. So there was no change in non-exercise activity. So it's important that you know how to interpret y-intercept and slope in the context of the problem. So the second thing you need to know how to do is to make predictions. So in this problem, it says this is the predicted fat gain for a subject with an NEA of 400 calories. So on the line is the prediction. So to calculate that number, we would just plug in 400 to our equation. So you type all that in the calculator. And you get 2.2129. So the fat gain, we predict a fat gain of 2.13 kilograms. My number's off. I just wrote down too many. It should be 2.1. So we predict a fat gain of 2.13 kilograms from the person with a non-exercise activity equals 400 calories. Again, you have to have the hat over fat gain, or in some cases it'll be Y hat, because it is the predicted value of fat gain, not the actual. If you notice, the actual at 400 falls at this data point right here. So that's the actual fat gain that someone had when they had 400 non-exercise activity calories. So if I asked you to predict what would happen when someone had non-exercise activity of, let's say, 2,000 calories, well, that falls really far off of our graph. We would almost have a negative fat gain. So this is called extrapolation. It's when you use a regression line for predictions that fall outside the interval of values that are on your scatter plot. These predictions are not accurate. So you can't make predictions using X values that are much larger or much smaller than those that actually appear in your data. It will not be an accurate prediction. So take a minute, pause the video, and do the check your understanding on page 167. All right, so the first one was interpreting slope and y-intercept. So the number one, the slope is 40. So the interpretation, we predict that a rat will gain 40 grams of weight per week. The y-intercept is 100. This suggests that we expect a rat at birth to be 100 grams. So number three, the predicted rat's weight is 740 grams. And then the third one, you need a little bit of an explanation here. So if you were to try and predict the rat's weight at 2 years using this regression line, that means you'd have to plug in 104 for the weeks. That means the rat's weight would be 4,260 grams, which is about 9.4 pounds. If you think about it, that's the average weight of a newborn baby. So you're saying that the rat is as big as a newborn baby. So this is unreasonable and is a result of extrapolation. 104 weeks falls way outside of our data values, so it would not be useful to use the regression line to predict that value. All right, so the next thing I'm going to talk about is residuals. So when we did histograms and we found the mean, we found the average deviation from the mean, and we got our standard deviation. So residuals are kind of have the same concept. We want to find the difference in the observed value versus the predicted value on the regression line. So to find the residual, you're going to take the observed y, or the actual y, minus the predicted y, or the y hat. So y minus y hat will give you a residual. So each black line in this picture is a residual. When you have a negative residual, that means the data point falls below the predicted line. When you have a positive residual, your data point falls above the predicted line. And the black lines, they are your residuals, but they're just, they're your deviations from the actual observed y value with the predicted y value on the regression line. So to have a least, we've been talking about regression lines, but to have a least squares regression line, it finds the smallest possible sum of the squared residuals. So it makes sure that the residuals are the smallest possible that they can be. So that's why your least squares regression line is your best fit. And that's why in Math 1 we called it line of best fit. You probably didn't call it a regression line. So here's an example. We'll do this one together. We're going to calculate the least squares regression line, interpret the slope, and then we're going to find the residual for a hiker who weighs 187 pounds. This data probably looks familiar because it was in yesterday's video. But we're going to go through the steps again on how to find the regression line. So go ahead and type this data into your calculator. Body weight goes in L1, backpack weight goes in L2. All right, now that you have the data typed in, you're going to go to Stat, over to Calc, and you're going to do the linear regression, number 8. So click on 8. Hopefully you put your X's in L1, your Y's in L2. If not, you just need to change it. And I'm going to store my regression equation in Y1. So I'm going to click Alpha Trace and click on Y1. So this just puts my equation into Y1 in case I need to use it later. So I'm going to calculate, and there's my equation. So my slope is 16.26. My y-intercept is 16.26. My slope is 0.091. And you can see the form at the top. It tells you how to write the equation. You would just plug in those numbers for A and B. So your equation looks like this. So now we're going to interpret the slope. Again, I like to write it as rise over run. If I have 0.0908 over 1 is my slope. So as my x's increase by 1, my y's will increase by 0.0908. It doesn't really make sense to talk about my body weight increasing by 1, so we would say by 10. So if I'm multiplying both by 10, that might be a better context to write the problem in. So this is what I have. The slope is 0.0908. We predict that if a hiker's weight increases by 10 pounds, that's your x, their pack weight will increase by, and that should say 9.08 pounds. That's a mistake. So the y-intercept, but never mind, we're not doing the y-intercept. So then calculate and interpret the residual for the hiker who weighed 187 pounds. So the first thing you need to do is calculate the predicted pack weight for that hiker. So you're going to plug in 187 for x and get out your y half, just like this. So the predicted weight for 187 pounds is 33.28. Well, then if we go back up to our data, 187, the actual backpack weight for somebody weighing that was 30 pounds. So to find my residual, I'm going to do 30 minus 33.28. So my residual is negative 3.28. So the actual data point falls below the regression line. So to interpret the residual, the regression line over-predicts the hiker's backpack weight by 3.28 pounds. So it predicted that it could carry 3.28 more pounds than the actual weight of someone who weighed 175 pounds. All right, so the next thing we're going to talk about is some formulas for least squares regression line. We know how to calculate the least squares regression line using our calculator when we have all the data. But there are times where we're not given all the data. We may be given the standard deviation of our x's and our y's. And so if we're given that information, we can use this formula to find slope. So this is kind of in the form, this is on your formula sheet, except on your formula sheet, B would have a subscript of 1. But R is your correlation, S subscript Y is the standard deviation of your Y values, S subscript X is the standard deviation of your X's. And it would tell you all of these values for you to calculate. To find your y-intercept, you do A equals y bar minus B times x bar. So you'd have to find your slope first before you could use the y-intercept formula. And again, this is on your formula sheet, except instead of A, it's going to say B subscript 0. So look like this. And you would have all the information. If it gives you the mean and standard deviation of X and Y, you can use these formulas. So here's an example. We're still talking about that same problem. Of course, we knew the data value, so we would be able to come up with the equation using our calculator, but we're just going to go through the work of how to do this if we did not have that. So read through the question. It gives you everything we need. We're trying to find the least squares regression line. So the formula for slope is R plus the standard deviation of y over the standard deviation of x. So R is negative 0.7786. The standard deviation of y is 1.1389. And of x is 257.66. Type it all in, and you'll have your slope, which is negative 0.00344. We already knew that because we did it on the calculator, but in a problem on your exam or on your test, you would not have your data to do this all the time. You would have to use this formula. So then to find your y-intercept, you're going to use this formula, y bar minus b times x bar. So y bar is 2.388 minus, and then we're minusing a negative, so let's just go ahead and change it to a plus, 0.00344 times x bar, which is 324.8. You type all of that in, and you get a y-intercept of 3.505. So then we would just write the equation. Y hat equals 3.505 minus 0.00344 x. And that's how you use those formulas. All right, the last thing I'm going to tell you about is a residual plot. Residual plots are really important, and we're going to go over in class tomorrow how to interpret residual plots. But all you have to do to plot the residuals is first find the residuals for every single value in your data. And I'm going to show you a quick and easy way to do that on your calculator tomorrow. So that becomes your x value. Your x values will that becomes your y values. So your x values will stay the same as your original data, but your y values will now be the residuals instead of the y values from your data. All right? So as long as you know what a residual plot is, we're going to go over how to actually do them tomorrow in class.